Good evening, everyone, and welcome to the keynote lecture on the first evening of this conference. It's a pleasure for me to introduce today's keynote speaker, Professor Marco Marengo, who is a physicist and a professor of thermal engineering at the University of Brighton, United Kingdom, where he also serves as the director of the Advanced Engineering Center. Professor Marengo is also an adjunct professor at the York University, Toronto, Canada, and serves as the associate editor of the International Journal of Multiphase Flows, as well as MDPI Energies. He leads the European Space Agency Pulsating Heat Pipe Scientific Team, and his research has been published in more than 350 scientific publications, among which more than 90 are in peer-reviewed international journals. His research focuses both on the fundamental and applied aspects of two-phase flow systems for space and ground applications, and also in the experimental and numerical modeling of phase change heat transfer, microfluidics, atomization and sprays, rock physics, heat pipes, and surface wettability. Today, he'll be speaking to us about some of his very recent work, and I would now request Professor Marco to take to the virtual podium to deliver his talk titled Diffuse Interface Modeling coupled with Fluctuating Hydrodynamics Theory for the Simulation of Vapor Bubble Nucleation. Over to you, Professor Marco.
Thank you so much, Ganesh. Thank you for this kind introduction. Let me share my screen, of course, so we can start. Let me only know if it's possible to see my screen and you can see my presentation.
Yes, your presentation is very clear, and anytime you would like to start, please go ahead.
I'm going to start. Yes, this presentation is divided in three parts. One is about the heterogeneous nucleation and the classical nucleation theories. The second part is about experimental results on wettability and roughness effects on pool boiling. And the third part is the diffuse interface modeling of stochastic fluid dynamics. What is interesting is that there is behind this presentation a kind of story about my research in the last 10 years. So, the motivation, I think that in this context, motivation are quite useless to present because everybody knows that the two-phase cooling systems are very important for many applications, from space application, aviation, data centers, electronics, and so on. So, and also this figure here is for this audience is very standard and is very clear. So, what I would like now to stress is that we are very interested in this part of the graph, so with the onset of the nucleation, so the onset of nucleation of boiling onset. So this is really what we would like to focus our attention. So let me take the pointer, so I think that so that everybody can see. Maybe I can use a laser pointer, so it's not bad. Okay, good. So let's start. So everybody knows at a given point we increase the temperature of the surface until a point where we have nucleation. Okay, very clear. Now, let's say something more about the classical nucleation theory. So nucleation in a liquid is a state of tension. This theory is quite old. You can consider that even there are papers of Huygens in the 17th century. But then there was formalized by Gibbs in the 19th century, so between 1876 and 1878, and then there were works from Forman and Weber, Becker and Doring, and 40 years ago was a very important work from Blander and Katz. What is important here is that we have a system at a given pressure and temperature. And the P-sat is the pressure at which we can start to have a phase transition. Okay, so the phase transition is happening when we have let's say the generation of a bubble, and we are really focused on this point. When a very small bubble is formed, we are speaking about nanometers. There are two contributions to the change of the energy of the system. One is the bulk, and the other one is the interface. So, and what is happening is that the bulk energy is decreasing because we have that the vapor has a much less energy per unit volume with respect to the liquid. On the other side, we have the interface energy, which is increasing because the interface between the bubble and the rest of the liquid is increasing in time. So in fact, we have an effect of increasing this energy. So what is happening then is that the interface free energy is increasing, the bulk free energy is decreasing. And if you think in terms of values, we have the number of atoms that are changing from liquid to vapor is varying with with R, so the dimension of the bubble, power to 3, while the area of the interface is going with R squared. What is happening then, mathematically, is that we have a maximum. At the given point of R, we have a critical condition where the energy is reaching a maximum value. And the critical value of this energy is happening when we have RC, the critical value of the radius, is equal to 2 sigma. Sigma is the surface tension, divided by delta P. So the difference between the pressure at the point and the saturation pressure. And also we have, let's say, the value of this jump, let's say, of the energy. So this is something important for us to focus on. So we would like now to understand what is happening when we have heterogeneous nucleation. The theory before can be applied for homogeneous nucleation, but when we have heterogeneous nucleation, the things are changing because we have a wall. So we have the presence of a third phase. And in particular, what is important for us is that there is a contact angle between the bubble and the wall itself. So the probability of nucleation of the vapor phase is written above, and it's very clear that it's linked to this jump of the energy, of the free energy, divided by kT. K is the Boltzmann constant. So one can calculate this kind of probability of nucleation, and one can see that what is important is how far we are from the saturation conditions. Not only, if you are considering the volume of the volume of the bubble has something to do with the contact angle. So it's very clear that the energy needed to introduce a bubble for the heterogeneous nucleation is pretty much influenced by the contact angle, so by the wettability of the surfaces. So you can see that the barrier is changing by a factor. This lambda factor is the change of the barrier to overcome in order to have a stable condition for the bubble inside the wall. So if the liquid completely wet the wall, theta, the contact angle, is equal to 0. And if you can see from this equation here, this means that lambda is equal to 1. So in fact, there is no change in the nucleation barrier. So this means that it's almost like to have a homogeneous nucleation. But on the other side, when we have, let's say, theta equal pi, this value is going to 0. So, in fact, theoretically, with an infinite jump in order to have a stable condition, okay, for, let's say, fully hydrophobic surfaces. So, whatever it is, the situation, what is interesting is that the critical radius is the same, okay? So it's always 2 sigma divided by delta P. And not only that, it's very clear that the roughness, so the dimension of the cavities on the surface and the wettability are playing a major role. There are problems with this classical nucleation theory approach. This approach is also called thin wall approximation. Okay, so what is important to say here is that we may improve this kind of approach with the so-called density functional scheme, because there are 2 issues in the CNT, in the classical nucleation theory. One is that the surface tension is not constant, but depends on the interface thermodynamics and thickness. So in fact, the surface tension is 2 sigma divided by delta P, but sigma is itself a parameter, is itself a variable of the problem. And the other one is that the energy barrier remains the same even if we are very close to the Spinolda curve, where it should be 0, because close to this condition, to the spinodal curve, you have always a phase transition. So, and this jump doesn't depend on the, let's say, the vicinity to the spinodal curve. So we can improve it. We can improve this situation. So this is a little bit complex, so I don't want to enter in too many details because I don't have time. But what is important is that one way to overcome the issue is that we are going to write the free energy adding one term. And the term is lambda multiplied by the gradient of the density square. So if we are adding this term, the total energy, the total free energy, is the energy that we had before, so half rho, but then there is this extra term. This is very important for us now, because lambda has something to do with the surface tension, and this gradient of rho means that if we are in condition where the gradient is very, very important, because we have a very steep, let's say, very steep means that in a very small area we have a very big change of the density, this term becomes dominant. So this is very important. So what is happening then is that we can do some treatment of this equation, and you can see, you can focus your attention here. This is the negative pressure of the system, and this is the thin wall approximation. And we are expecting that at some point that the energy barrier is going asymptotically to zero, close to the spinodal conditions. But what is happening? That the thin wall approximation is decreasing, but it's still finite. So the density functional theory in this sense is much better, because this means that if it's going to zero, all the bubbles, even the smallest bubbles, are critical close to the spinodal curve. Imagine that the spinodal curve here is about minus 6.5. So asymptotically, the energy barrier is so small that you have always bubbles that are stable in this condition. And this is just what we like to have, okay? Not only that, as I told you before, that lambda and this free energy are able to define the surface tension. So the surface tension is not anymore a constant, but depends on these parameters. So this is really a big step forward. So it's very clear that the surface wettability is indeed very important for our pool boiling and onset nucleation. So we started many years ago. I started to work on that, let's say it was 2008, 2009, I think, so 12 years ago, 13 years ago. We wanted to understand which was the effect of the wettability. There were a lot of works about that, but was very difficult to divide the effect of the wettability with the effect of the roughness. So what we have done is that we use a chemical method in order to graft the surface with hydrophobic molecules. Why is that? Because if you're using, for example, glass or a very smooth surface, putting one layer of molecules is not changing, of course, the roughness. So the roughness is the same as before, but we are changing the wettability. So this is the way to change the wettability without changing the surface roughness. And so for us, this was the breakthrough. So we can cure the surface and we can obtain a hydrophobic surface or hydrophilic. So we did experiments on non-grafted and grafted surfaces, or when grafted only one point and so on. And in fact, we saw that there is a very important effect linked to the hydrophobic surfaces. So when you're using hydrophobic surfaces, we have a very strong decrease of the onset nucleation temperature. So for example, using a very smooth surface, we have hydrophilic surfaces where the temperature, the difference of temperature between the temperature of the wall and the saturation temperature is 9 degrees, and other that are 5 degrees. So with hydrophobic surfaces, we have an effect. But then we got a problem. And the problem was that, in fact, we did the same experiment using very, very smooth surfaces, polished surfaces, where the roughness was 10 nanometers, 7 nanometers. We did this experiment, and this was really a bad surprise for us because, look, we have three different superheat, even if the surfaces for us were the same. We're with a very small roughness. So the problem was that the mean roughness was not appropriate to describe the topography of the surface. In fact, if you're going in this direction with the difference in peaks of the roughness, or in fact this is the measure of the cavities, you can see that the cavities are really different. So it's 45 until 95 nanometers. However, we have still a problem. And the problem is that looking at the classical nucleation theory, we should have had 150 degrees of superheat, but we had much less. As you can see here, we had 10 degrees of superheat, 12 degrees of superheat. So this was puzzling. So how is possible that when we are considering a super smooth surface like that, when we have a critical cavity radius which is, for example, of a few nanometers, we should have 100 Kelvin of superheat. Look at this, 100 nanometers, and here we should have with water, we should have 300 degrees. So we are going in the direction of Spinolda condition, homogeneous body. But it's not the case. Why that? So we have a mystery here. We have a mystery of low onset when we are dealing with water in these conditions. So the classical theories are not really able to understand what is happening. And there is no theory yet. Okay? So in order to overcome this problem, we went in this direction. We tried to understand if it was possible to use the fluctuating hydrodynamics plus diffuse interface modeling to understand what was happening at the mesoscale. So we start with the same equation that you saw before. So we have here an additional term. The only difference with respect to what I said before is the factor 1/2 here. So there is a number 2, but in fact it's really the same situation. So the free energy depends on this gradient of the density from the vapor to the liquid and the dimension of this region. Okay? So lambda is now a phenomenological parameter related to the surface tension itself, of course, but also to the interface thickness, which can vary in the different conditions. We can write a new equation here. So we can write the equation that are the classical Navier-Stokes equation, but we can add a phase change and latent heat, and we can have the capillary stress. So we are adding this term. See that this term here depends on the gradient of the density, as I said to you before, and depends on lambda. So in fact, the stress here depends on the surface tension and the interface dimension. Okay, this is rather important. This is a change of the physics inside the Navier-Stokes equation in this sense. Of course, we have also this term, which is related to the phase change and latent heat. So, on the other point, we have that there are fluctuations. There are fluctuations to consider. And the fluctuations are linked to the fact that density, velocity, temperatures are changing because of the molecular, let's say, walks. So the molecular paths inside the system. So if you're considering the microcanonical conditions, one can write the entropy in this way. So you can write the entropy in a way that is considering the fluctuation of the density in this way, the fluctuation of the velocity, and the fluctuation of the temperature. Okay, so this is the so-called microcanonical ensemble for isolated system. There is no change in mass or number of atoms. There is no change in volume. And there's also no change in energy for these particular conditions. So, what is happening now? It's happening that if we are doing this kind of simulation, we are landing to something like that. It's from a YouTube, Paul Otzeberg. This is very nice picture of what is happening. And we are landing using an approach that is due to Landau and Lifshitz, is a so-called Landau fluctuating hydrodynamics. What is important here is the correlation of the fluctuation. So in this case, we don't want that we have a correlation between the density and velocity or density and temperature. However, we have a correlation function for the density with itself, or the velocity or the temperature, for points on the region. So we have a local correlation. Okay? We have local correlation. Pay attention that for velocity and temperature, delta is the delta Kronecker. So when x is equal to x first, this is 1. All the rest is 0. So in fact, velocity and temperature has only a local correlation, they are correlating only locally with a given value. But what is happening with the density? Well, the density, there is a distribution. So there is a diffusion of the density in terms of correlation. If you're thinking that the density is changing 1 point, this effect will change also the density at another point. Of course, not so far. So there is an exponent, there is a decay. But in fact, there is an effect. So what can be done then is that instead of this equation, we can add also one part linked to the fluctuation, the stochastic forcing. So in this case, we are going to have a noise operator. This part is a new part, where we are taking into account a Wiener process that in fact indeed a Brownian motion, is a Brownian motion. So we are considering fluctuation following a Brownian motion. And so we are landing with a non-deterministic capillary Landau-Lifshitz-Navier-Stokes equation, which is pretty complex. I don't have time really to explain. It can take maybe, let's say, a few hours to explain all the mathematics behind this. But what is important is that in this case, we can do, let's say, the simulations. And then what is happening? Well, in our system, the bubbles are formed naturally. So we don't need to put the bubble inside. These are due to the fluctuations. And also the growth in the bubbles is linked to the thermodynamics. So to the effect that we are reaching a given critical radius. Here is the number of bubbles in time. And you can see here that we have really a number that is increasing and decreasing. And the number is decreasing because we have coalitions of the bubbles. And this is the value of the density, 0.46, 0.48, which is inside the range of this dimensionless condition between the spinoidal and the saturation. So we are between the spinoidal condition and the saturation condition of 0.51. Of course, if you are going to increase this value, we are going to increase the density. So this means that we are closer to the saturation points. The bubbles are becoming less and bigger, okay, because of the coalitions. If we are closer to the spinoidal, we have a lot of bubbles because, of course, the free energy jump is much less. What is happening then is that we can try to understand also in terms of the comparison with the molecular dynamics, because we are very close to this approach. One thing that one can say is that here, this part is about 300 nanometers. So this cell here is a cube of 300 nanometers. We have submicron condition. Okay, so the problem of using molecular dynamics, of course, that the computational cost is really much bigger than what we can do. Here, you can see that, for example, we have our values in contrast with the classical nucleation theory for the nucleation rate. And one can see that if we are closer to the spinoidal in this condition, our approach is much better because, in fact, we have a decrease of the value of the, let's say, of the nucleation rate. So, and we are really, we can compare this with the molecular dynamics in some sense. So, it's very interesting now because this is really the key point. So we have a nucleation rate and we have a volume dynamics, right? So what is happening? That sometimes you see here, this is the volume of the bubble in time. You see these jumps? the jump, is due to the coalitions, due to the collision of bubbles. So the bubbles can jump from one volume to another because of the coalition and collisions. So if you are doing this kind of simulation, what is very important is that the classical nucleation theory are only considering one single bubble. But when we have more than one bubble on the surface, what is happening is that we have coalitions. So we have collisions, and the collisions are increasing the bubble radius higher in a direction that is higher than the critical volume. So the fact that the bubbles are not isolated, the fact that the bubbles are, let's say, surrounded by other bubbles, is indeed decreasing the bubble radius, the critical radius. This is the point. And we didn't think about that, but this is very, very important for our understanding. So, in fact, what is happening? Also, the average temperature on the surface is a function of time at the different heat fluxes. So, depending on the heat flux, here we have the different condition, and we are going to increase the heat flux in this direction here. We can, in fact, if we increase the flux at a given point, we are increasing the onset temperature, but of course the number of bubbles is increasing. So these local maxima here correspond to the appearance of the first large vapor embryo. So is the onset temperature. So this method is able to indicate how much is the onset temperature as a function of the heat flux. And we found that the onset temperature is in fact a function of the heat flux with a power law, which is also an interesting point. So the explanation then is that is the bubble clustering at the nano size, which is in fact influencing the onset of nucleation. Do you remember this picture I had before, where I put even with nano cavities, you have a very low temperature of the onset, very low, much lower than the homogeneous temperature and the spinodal temperature. Why? Well, what we can say is that indeed the problem is that we have a cluster. If we are producing a cluster, and we measure here the tendency of the clustering to the radial distribution function, okay, if these bubbles are close, then they are going to merge. So the cluster bubbles means that we have a high probability of bubble coalitions, enhancing the bubble growth. So this bubble-bubble interaction is usually neglected in the available theoretical models. So the temperature onset is reduced because of the bubble clustering and collision. And we did the calculation. So imagine, here is the bubble radius. This is, for example, what is happening in terms of bubbles that don't experience any coalitions. And these are the bubbles who merge with the other bubbles. So you see that there is a very strong increase of the bubble dimension. So the number of bubbles is increasing because of the coalitions. So if you are looking at the effective critical radius, in fact, look at this figure. This is the flux, and this is the critical radius. And this is the distance between the temperature minus the saturation temperature, and then here is the difference between spinodal temperature and saturation temperature. What is happening? Well, in the classical nucleation theory, for this flux, you are expecting a 0.8 for the temperature of the wall to initiate the boiling. But if you are considering the onset, is 0.611. So if you are considering even the classical radius, the radius linked to the coalitions of the bubbles, this is the same for a very low heat fluxes, but is strongly decreasing when we have a high flux. So this means that when we have a high flux, we can have a stronger decrease of the saturation of the nucleation temperature with respect to the classical nucleation theory. So this means that indeed, instead of having, for example, 200 degrees to produce the bubbles, we need only 10 degrees or 20 degrees. This is, at the moment, our explanation. Conclusions. Of course, this is still a running journey in the physics of boiling on set. But it's very clear that boiling on set is influenced by the wettability. Even if we have a very, very smooth surface, ideally smooth surfaces, we had an explanation using molecular dynamics. Lower wettabilities increase the mobility of the molecules on the surface, decreasing the energy barrier. So this could be a possible explanation about the wettability. But there is still the mystery of the very low temperature, onset temperature. The value of the boiling onset temperature is much lower than the value predicted by the classical nucleation theory. And our explanation using the stochastic fluid dynamics and diffuse interface is that the clustering effects are really the most important parameters. And this is what is generated a very strong decrease of energy barrier. So of course it's not really, let's say, decisive, no? A breakthrough in terms of, we are not so secure that everything is like that, but we saw that this effect is pretty important. And so the final point is that the use of nanoscale modeling of nucleation, using this diffuse interface modeling with stochastic dynamics, is opening a new unexplored route for the multi-scale modeling of nanoscale boiling processes. So thank you so much, and this is a book where you can find also all the information about this lecture. Thank you so much.
Thank you, Professor Marco, for a very interesting talk. Now the floor is open to questions, so I would request the participants to ask their questions to Professor Marco Marengo. Professor Marco, as we wait for some of the questions to come over, I have a couple of interesting questions. Just wondering, when you talked about the classical nucleation theory, you were talking about a static contact angle.
Yes, it's not called static, it's called equilibrium contact angle.
Right, okay? Exactly. Yeah.
The equilibrium contact angle, yes.
Right, yeah. So in your simulations, so it does account for the dynamic contact angle, I believe, right?
No. In our simulation at the moment, it's still an equilibrium contact angle.
It's still
we are not considering advancing and receding contact angle. Honestly, the velocity we are speaking about in terms of growing, they are not so high. Say. So in this sense, there is it can be there is an effect, but I don't know. At the moment, it's not our main worry.
Okay. Yeah, I get it. Yeah, I was just also wondering, what are the initial conditions for your simulations? I mean, how is it that you initiate the simulation and you get these bubbles?
Exactly. This is interesting because usually when you're doing, for example, a lattice Boltzmann simulation or a VOF simulation, in the lattice Boltzmann you need to put the temperature of the set, and then the VOF you need to put one bubble.
Right, yeah.
You put one bubble and then you have the rest. In these simulations with the stochastic fluid dynamics, you don't need to do that because you know what is happening is really that the fluctuations themselves are producing
the bubbles.
They are generating the bubble. So it's really natural. It's really what is happening there. So the condition is very simple. You have a cube, 350 nanometers, 500 nanometers, like that.
Right. Yeah.
And at a given temperature and pressure. So it can be somewhere, let's say, with the pressure. What is important to say that we are close, maybe we are not so far from the critical point, but the reason is that if we are very low with respect to the critical point, the simulations are very long. Because the fluctuations are not so strong. So you need to wait a lot of time before you have the first bubbles, you know? So if you're going up, the physics doesn't change, but of course you can see the bubbles appearing very fast. Very fast means after a couple of days of simulation.
I get it. Yeah.
But it's already something. But what is important is that bubbles are formed, let's say, like that, naturally, spontaneously. You don't need to set any temperature. You don't need to set any bubbles before. You don't have any seed.
Yeah, thank you. Another question. So you were talking about very smooth surfaces, right?
Yes.
So how do you incorporate surface roughness in the simulation level? Do you have to geometrically model the roughness, or
The point, Ganesh, is that we don't want the roughness. In the
oh, okay.
sense that what we would like to see is the effect without the roughness, as I saw you. Because
Ah,
the point was, the mystery was, when we have a very, very flat surfaces,
right.
no, we are expecting the temperature for the nucleation is
Very
200
high.
degrees,
Yeah,
no,
yeah.
with
True.
respect to
Yeah.
the saturation. And
Correct.
no, it was 10 degrees, 20 degrees.
Yeah.
If you run the experiments, it's always very low. Why? So we didn't want to have the roughness. It's the opposite.
I get it.
In,
Yeah.
in principle, it's possible because we can have, we can put some roughness cavities and so on. But of course, what is happening? Then they are going to dominate. So of course, if you have roughness, then you produce the bubbles there. The bubbles is growing from the cavity, and so
Correct.
you don't see this effect. So for us at the moment is less interesting. So we would like really to have an ideal surface and to look what is happening in terms of wettability
Okay.
and nucleation rate.
Right. Just one last question from my side. Just wondering, if you introduce surfactants in the flow,
Yeah.
how do you incorporate that in your simulations?
Usually what the surfactants means that you have a lower surface tension. Okay.
Oh, okay.
So yes, and so you have the contact angle usually is lower.
Right.
Okay, or with respect to the liquid, because
Right.
the other one is
Yeah, true.
The bubble is different. But with respect to the liquid, the surface tension is lower, the contact angle is lower. So
Yeah.
for us, there is no big change in the sense that we need to tune lambda.
Right.
We can put lambda. We are going to have a lower surface tension.
Right.
And this is done. So we can do the simulations.
Yeah. So once you tune lambda, the fluctuations then take care of it, right?
When we're tuning lambda, we are tuning the sigma, so the surface tension. This means we are tuning the critical radius, because the critical radius is 2 sigma divided by delta p. Okay,
and you're tuning the interface thickness as well.
The thickness is a one output of the simulation.
Oh, okay.
Because the gradient of rho is the output. The density variation is an output. So when you are close to the spinoidal, of course, the interface is much bigger. So you have this kind of very strong diffusion between the liquid and vapor, right? Oh. It must be like that, in fact. If you have a fixed dimension of the interface, you are coming back to the old classical nucleation theory, where the free energy doesn't depend on the closeness to the spinoidal point, and we don't want that.
Right. Yeah. Thank you, Professor Marco. So we have a question here. The question asks, it says, "Thank you, Professor, for an interesting and informative talk. Can you give some insight into the computational clock time taken to run each simulation?"
So our simulation are going to have a time step of 1 picosecond. Okay. Okay. So 1 picosecond, and then of course, say to have the first bubbles, you need to reach about 1 microsecond, something like that, or even less. Let's say it depends on the conditions. If we have a very high heat fluxes, we can still have some formation at the very, very beginning, so nanoseconds. Okay, so after, let's say, 1,000 time steps, we can see the bubbles, depending on the condition. This is the reason why we are close to the critical temperature, because it's much faster. Otherwise, you need to wait. Imagine to have a condition. You have water at 110 degrees with the surface there. So you're going to produce bubbles, but maybe it's 10 microseconds. You need to 10 microseconds. So if you're starting with 1 picoseconds, you need to have 10 million time steps before you have the first stable bubbles. And this computationally is becoming very long.
So I believe we don't have any further questions at the moment, but I'm sure that all the speakers would have really enjoyed your talk, which took us from a very simple introduction, starting with the classical nucleation theory all the way through your experiments talking about the anomaly and how fluctuating hydrodynamics has helped to partially resolve it in your own words.
So it's a kind of story.
Yeah, it was really an interesting short story, and I hope that those who are interested in this area would probably like to, of course, can't meet you in person at the moment, but definitely they would contact you over mail or other sources to hear from you as well.
Thank you so much, Ganesh.
So thank you. Yeah, thank you, Professor Marco, for joining us in this conference and giving this very exciting talk. And despite your busy schedule, I understand it's Christmas around the corner, but nevertheless, thank you for dropping by. And hopefully, when normalcy gets back, we hope to see you sometime in India soon.
Thank you so much. Thank you so much, Ganesh. Yeah.
So
you have a very important Indian name, Ganesh, right?
Yeah. Thank you. Yeah, thank you, Professor Marco. So on behalf of the IHMTC committee, I would thank you once again for taking time out from your schedule to deliver this talk. And I also thank all the participants who were part of this keynote lecture. See you all tomorrow. Thank you all.
Thank you.
Bye.
Thank you so much.
Thank you, sir.
Yeah, so Sasit, so I think we can close the session, right?
Yeah, we can close the session. Yes, sir. Thank you, sir.
Thank you. Bye.